started last week, and because of this, I will wrap up very briefly about early stopping, which was the first technique we discussed last time. I'm sorry that yesterday you had to do the exercising online. I don't know if Francesco has explained why, but basically he has a sore throat and a cold since a couple of weeks, and I think that COVID time is not the right time to send a person with coughing in a class, not to let's say make people uncomfortable. So we decided that the best things to do is to play on the safe side and do it online. But just to clarify, Francesco is okay, so don't think he's sick or things like that. But I mean, we want to take all the, let's say, safety procedures of the case, and we decided to postpone this. From next week, we should go online, sorry, in presence as usual on Tuesday, and on Tuesday, Giacomo Boracchi will start talking about images. I mean, so far with today's lecture, we have basically done the foundation, I would like to say. And after the foundation, we will enter two main domains. One is the image domain and the image classification, recognition, and many other tasks to be performed with images, while I will come back later on discussing about sequences, and in particular, I will talk about a little bit of text and how to use these models on text. Indeed, probably the two most, say, the fields where deep learning and artificial neural network now have impacted the most are image understanding and text understanding. And the reason is because they are unstructured first, and second, because it is hard to define features in these domains. So having a lot of data, it is possible to extract. There is another field where deep learning nowadays is, let's say, having a lot of attention, dragging a lot of attention, and it is basically setting the standard is graph. So performing machine learning on graph structure. So what are called linked data with the reference to images, text, and audio, and linked data as a set of unstructured data where deep learning is working the most. Unfortunately, we cannot have everything in one class, in a single course, so we will not discuss about linked data within this class. Yes, I will record the lesson. Thank you for reminding me. I was waiting for people to show up, and then okay, just I would like to do one more thing, which is to set up my system in such a way that I can control it better. I know you're seeing strange things on the screen. Don't worry. It is just me playing a little bit with the Windows. So let's see if I have or okay. So let me start the recording. By the way, on the course, we are perfectly aligned. So currently on the course website, you have links to all the recording of all the lectures except yesterday. I mean, yesterday has been recorded by Francesco, so I need to get the link and post it on the course website. But knowing Francesco, I will get the link today, and everything will be set by the weekend, where I know that many of you are studying, because I get the messages during the weekend about the slide. When will be more or less the first assignment? That's a good point. The first, probably this is something that you want to record, so I'm taking it as a constant. So I'm starting recording the lecture now. Today, I would like to finish the foundation part on neural networks. So I will discuss about mainly two things. One is overcoming overfitting, which means continuing from where I left last week. The second part is about a couple of details, which are activation function and initialization. This closes the foundation. After that, we are going to have lectures on image analysis. And after Professor Boracchi will have introduced image analysis and convolutional neural networks, we will have the first assignment. So the first assignment is about classification with convolutional neural network, and thus I expect you to attend the classes on convolutional neural network before we can just, let's say, give you the homework. Okay, going to start now. What I would like to do is to catch up a little bit briefly on where I left last time. As I said, this course is about neural network and deep learning. We might have at the end of the course special classes on special topics, but this has not been decided yet. So, for instance, I'm thinking about part of these, for instance, how to make this network on hardware, or how to have network working on graphs. I have a friend of mine from a company that would like to come and talk about using neural models to perform anomaly detection. So I might have a set of seminar, which are not mandatory. I mean, they are free for you and you can attend them, but I cannot promise them yet. Okay, where did we left last week? I will stop my video for now, and I will focus on the slide. As usual, feel free to drop me some question on the chat. If I don't answer immediately, don't worry, it's because I will probably answer this question later. So what is the problem of overfitting? The problem of overfitting is the fact that neural networks, but this happens with models in general, might be too powerful. And because of this, they are very good in fitting the training data, that is minimizing the error function on the training data. But then when it comes to produce an output on new data, basically they do not perform as expected. And this is called lack of generalization or overfitting. I mean, if you see the fact that you're going too well on the training set with respect to the test set, is called overfitting the training set. If you think about not going to perform as well as you would like in the test set with respect to the test set, you call it lack of generalization. But more or less, this is the what is this due? This is mostly due to one specific thing, which is neural network are universal approximators, and you might end up easily building neural network with million of parameters. Million of parameters, it means that they are so good in approximating your data that basically they are able to drive your error to zero. And this is, last time we have seen this point, one of the typical issues that we see when we have overly complex neural network. So, for instance, when we have an overly complex neural network, the more you train, this is what K means, so the more training epochs you are going through, well, the more likely is that you will overfit the dataset. So, if you have a neural network with thousands, millions of neurons, at some point, it might happen that you will be able to draw the error to zero. Setting the error to zero, it's good in theory, but in practice is not. And the reason why it is not good in practice is that what happens is that the network has a zero error on the training, but when you test on, for instance, some holdout data, what happens is that what you get on the training set is not what you get on this holdout data. In the neural network literature, this set of data that you have extracted from the training data is called validation set. What you expect to see is that at some point the performance of the validation set and the performance of the training set will diverge. Will diverge because probably at this point the all the information, the deterministic information that could be extracted from the data have been extracted by the universal approximator, and after that what you get is just fitting the noise in the data. And this is something that basically you don't want to have, because what you get at the end is that your validation data, which is about overfit, which is about result on new data, is very different from what you expect. So when we see that our holdout set, which is a set of data that we are not using for training, diverge from the training, we can stop the training and we report that model as the best model that we could train in this way. When I say stop the training, I mean that we have seen that training is performed via gradient descent. Basically, when you find that the validation set error diverge from the training, you stop the gradient descent iteration, and then because of that, what you get is that you keep the best generalizing model so far. Okay, so what is this error that we get? We can think about this error, which is the error that we get when we stop the training, as a proxy of what will be the generalization error on what we called the test set. What is the test set? The test set is a set of data that I have really never seen, because to some extent the validation data have been seen, because this point here, which I stop the training at, is optimized with respect to this error. So in general, what you could expect is that if you plot, let me try to do this by hand. If you plot, no, I didn't want to do this, just a second. The test set data, what you would get is something like, just a second, is something like this. So this could be the test set error, which will probably follow the validation error. I mean, I'm expecting of this, but it will not be exactly the same of the validation error. This is what you observe in practice, but they are very similar, and because of this, if you optimize for the red line, which is the validation error, basically you will get a good test set error, which is data that you have never seen. So this, let's say, ES stands for early stopping, can be thought at the proxy, an approximation of what would be to what would be the result of this model when facing new data. Because of this, you can use this information, which is the early stopping error, to make some choices. So, for instance, to make some choices about how many neurons I should put in my network. Why? Because the network can be optimized under different perspectives. During training, you optimize the weights, but during design procedure, you can try to optimize how many neurons you have in the layer. So you can test with one neuron, you can test with two neurons, you can test with as many neurons as you think they are useful, but then you have to make a selection. One possible way to select how many neurons to put in the network is to make a lot of tests. You make a test with one neuron, with two neurons, with three neurons, with five neurons, with 1,000 neurons. But then you have to decide which one is the best model. And the early stopping error, which is the error on the validation set, is a good proxy for deciding which model is the best one. So one thing that you will find yourself doing is doing a lot of experiments. So you will test, for instance, with one hidden neuron. So this J1 is the layer, the first layer on the network. You will test maybe putting one J neurons in one layer. So, for instance, you put like here one neuron in one layer. This is probably the simplest network you can get, and you will figure out that when you put one neuron in one single layer, your network will have a certain validation error. Then you had 100 neurons in the hidden layer, and you get a network with a different validation error, which most likely which will be lower than the validation error that you got with a more simpler model. And you can go on. So, for instance, here I have put two hidden neurons in my network. I train it from scratch, and I get a different stopping point. So here, this second point that you see, that you see here, this second point that you see in the plot has been obtained by training a new network with two neurons. Then you train a third network with 5 neurons, and you get a different validation error. Then you keep enlarging the network, and what you observe on average is that the more neurons you add, the lower is the validation error up to a certain point. Why up to a certain point? Because what you get is that if you add neurons, the training error will go to 0. But the validation set will say, no, you are overfitting. The best you can do is this error. So before 5, the model was underfitting. It was too simple, and so adding neurons one after the other helped in reaching a better result. After 5, the model is not able to reduce the validation error. It means that the more neurons you add, the more the network overfits. But thanks to the use of early stopping, you stop the network at the right time. You will probably stop it earlier than expected. If we add neurons and we retrain, we might end up to have different values of key k. So we stop it earlier. I did an experiment recently. I don't know if Francesco did something about this, but I did an experiment by testing with different models and by trying to increase the generalization. What I find out was an exercise for a class is that basically these two curves, the training and the validation, have a totally different shape in a sense that they are more steep. And what happens is that the epoch at which you stop might change significantly. So there was a question in the chat. When you add a new neuron, we have always different k. Yes and no. I mean, in principle, yes. Don't get surprised if the model stops exactly at the same point. I mean, for a significantly different model, you should expect significantly different k. But also, if you train twice the same model, you might get that it stopped not exactly at the same epoch. Why? Because if you have used a different random initialization, you might have converged to a different minimum, and thus what happens is that you end up in a slightly different number of epochs. Usually, you don't care about this. I mean, you don't care about this because what happens is that you leave it, you run it, then you go to sleep. If it's a big model, you go back. If it has stopped, you look at the result, whether you are happy or not with your validation set error, and that's it. You don't reason about how long you have been training and so on. Okay. One question is, so in this example, after 5 neurons, one would need more data to make use of the additional neurons. Yes and no. So if the new data, they only add variance, what does it mean? It means that they don't provide more information. Probably you will not reduce this error. But in general, yes. If you add the data, then with more data, you might need a more complex model. So I will not look at this picture as how much data I need to fit such a big network, because this is a very complex question. I will reverse the question and say, how big how big I can make my network before overfitting this dataset, because at the end, I mean, it's the dataset that decides. If the dataset is not informative and not big, there's nothing you can do. You can either uh, reduce the size of the model, or you can keep it big but prevent overfitting with this technique, which is early stopping, or you can use one of the other techniques which can be used to improve generalization. And that's exactly what I want to talk about now. Today, I would like to continue talking about other techniques to improve generalization. One question, if we have more than one hyperparameter to tune, so not only the number of neurons in the first hidden layer, are there systematic techniques for finding the best configuration of the hyperparameter space? Yes, there is one systematic technique, which is try them all. That's the technique which is systematic. The problem is that it is unfeasible because the number of combination might not be, let's say, reachable in terms of experiment that you have to run. So one thing that you do, you sample the parameter space. So for instance, let's assume that you have two hidden layers and you don't know how many neurons to put in each of the two. You start saying that you put in each of them 1, 2, 5, 10, 20, 50, 100. This is a sampling of all the possible numbers that you can imagine for each of the two. Now you see that this makes a sort of grid on all the possible combination of neurons in the first layer, neurons in the second layer. And that is why this technique is called grid search. So you have to search on the grid what are the best hyperparameters. It could be an hypervolume. So, I mean, hyperparameters might be a lot. You can even think about an automatic procedure which samples this space of hyperparameter in a more or less intelligent way. You could use some Monte Carlo sampling, you could use some genetic algorithms, you could use some Bayesian optimization technique. I mean, but the search space becomes so huge that unless you're doing very toy example, you cannot search this space exhaustively. So the systematic technique is to find a way to sample in an intelligent manner the hyperparameter space, finding which are the most promising one. And that's the thing that you will end up doing if you want to do this job. So what happens is that you start from very small models, then you will increase until you get the overfitting. And once you get to the overfitting, you say, okay, now I have to uh, improve the generalization capability. How do I improve the generalization capability? First approach, early stopping. So you keep a big model, but you use a validation set to prevent that this big model overfits by stopping it earlier. Okay, I mean, this is not something brand new because this was the ending of the last lecture, but I would like to start from here to discuss how can we improve on that. Okay, let's start saying that early stopping is my personal favorite technique to prevent overfitting. Why? Because it simply works. And basically, what it does is compensating for every over estimation of the required parameters that you might have put in the net. But it has one drawback, one important drawback. You have to set apart a validation set, and you will not use this validation set data. So at some point, you will reach the point where you have tried them all solution, and what you would like to do is to see, as your colleague was suggesting in the chat, if adding more data will make your model work better. The problem is, where do I get more data? So more data, either you buy the data, are in the validation set error. So, in a sense, validation set are data which are wasted because you will never update the, let's say, you will never update the weights of the network by using the validation set. You will always use the test set error. And don't think about rotating this data, like saying, oh, I will do one epoch with some data, then I shuffle them. This is a very, very, very misleading approach, because if you start using any single point of the validation set to update the weights, what happens is that you overestimate the performance of your model. So how can I use all the data and at the same time prevent overfitting? One question, subsampling is bad? Well, subsampling per se is not bad. You can take validation by subsampling with replacement the training set. But then you don't use it for training. I mean, if it's a validation set, it's a validation set. You should never use this data to update the weights. That's a very important aspect. One question says, I don't understand why in this data, after 5, this point, is it correct, the question? I don't, just increase. Oh, okay. Some of you were already confused by this last time. I wanted to do this, that is to put a higher error here, because you should think that these are real data. What does it mean? That you put 5 neurons, you train this model. You put 9, you reinitialize the model, and you will end up with a model which is better than what you expect, because the result depends on your initialization. I mean, one thing is the theory, but then you go to the practice. You can get a point like here, where my pointer is, or you can get a higher. Don't get surprised that especially with very small sample, so when you do not repeat the experiment many times, results are against the theory. Well, the theory is a stochastic thing. I mean, it means on average, it behaves like the red dashed line, the red row there. Not it has to do that. I mean, it is. It has uncertainty. It might happen that here, just because you reinitialize the model from a different init point, you get a better result. Okay, so I hope that this has clarified everything about early stopping. What I would like to discuss are other forms of generalization. So other forms to improve the generalization capability of a model. After the early stopping, the most famous way to improve the generalization capability of a network is to perform what is called regularization. So what is regularization? Well, let's assume that the presence of many parameters makes the model very, very, very flexible. This means that the model is free to bend and fit every single data point. What you would like to do is to limit this freedom of the model, and limiting this freedom of the model, what you would like to do is to limit the probability that this model will be able to overfit the training set. So basically, the idea of regularization is to constrain the model capability of fitting the data, and by this improve its generalization. For the one of you that have taken the machine learning class, I'm talking about the trade-off between bias and variance. You limit the power of the model, the flexibility. What does it mean? It means that you increase the bias of the model, but at the same time you reduce the variance, because the freedom is the variability of your model, and by increasing the bias, reducing the variance, you might get a better performance of the model. Why? Because the expected generalization error is given by the sum of the two. Not the sum is bias square plus variance, but there is this trade-off. For people that have never taken a machine learning class, basically the sense is that you limit the capability of the model of going through all the data points, memorizing the data point. There are different techniques for regularization. The, let's say, easiest, well, the obvious one is to put less parameters. So one extreme regularization is to reduce the number of parameters. In classical machine learning, this is performed via feature selection, via model selection. In neural networks, what you do, you remove some of the links, some of the weights, you set some of the weights equal to 0. Another approach is not to reduce, not to remove entirely the weights, but try to shrink those weights down. And how you do this? You make some assumption about the fact that they should be small. This idea is basically can be framed. What does it mean? Can be framed. You can interpret this idea under the so-called maximum a posteriori approach. So, so far we have found the weights for which the probability of the data was maximized. We have been talking about maximum likelihood estimation. We have seen that most of the loss function that we have been using so far, like the mean square error or the cross entropy, are the solution of the maximum likelihood estimation problem. They maximize the data probability. So basically, they only look at the data fitting, because the data probability, so the optimization, is performed by only looking at the data probability. So there's no way, if you optimize the data probability on the training set, fitting the data perfectly is the best thing you could do. And because of this, then you have to somehow hack the optimization procedure with the weight decay. Sorry, with the early stopping. What about writing a different loss function, or a loss function which basically generalizes by construction? We will see that is not that easy, but in principle, you could decide that you don't want to find the best fitting of the data, leaving the weights free. You would like to reduce the freedom of the optimization algorithm in looking for the weights. With early stopping, you can imagine this freedom to be limited by the fact that someone else will say, stop it now. That's not the best mean square error that you can get, but you have to stop here because then you're going to overfit. An approach which is based on statistics to include this limiting of the freedom of your parameter is called Bayesian approach. So it seems more or less the same thing, but according to the Bayesian approach, you can find the most likely weights given the data, which is very different from the weights which maximized the likelihood of the data. Why this is different? If you write what does it mean to maximize the probability of the parameters instead of the parameters of the data, by using the Bayes theorem, you find out that the probability of the weights given the data are basically proportional to the probability of the data given the weights. And this is exactly what we have been doing for maximum likelihood estimation, times your a priori probability about the weights. So this a priori probability is somehow shaping the search space for your algorithm. So what you're saying is that I think that the distribution of the weights, that is the distribution of my parameter, is like this. Taking into account that the distribution of parameters should be like this, now you can optimize the probability of the data, but you have to take into consideration my prior distribution. Prior, where it comes from? Well, there are different ways of designing priors. Most of the ways of defining priors are based on two things. Some knowledge that you will like to put into the algorithm. Second, some, let's say, opportunistic way of writing this probability distribution. What do I mean? I mean that to find this prior, we have to invent a probability distribution which first makes sense. That is, it describes some heuristic ideas. Second, which makes the computation easy. These two approaches, maximum likelihood, which is maximizing the probability of the data, and maximum a posteriori, which is maximizing the a posteriori probability of the parameters given the data, are two possible ways of training a model or fitting a model or finding the parameters of a model. And the real difference between the two is that in the first approach, data are the only piece which matter. In the second, you can say something about the weights that the algorithm has to take into account. Let's make an example. We know from, let's say, theory that, or actually not from theory, but from empirical observation, is that small weights improve generalization of neural network. So what we would like to do is to basically push the flexibility, reduce the flexibility of the model by limiting the, let's say, space of weights that your algorithm can traverse in seeking for the weights. So this is an observation from many, well, actually this was the observation upon which the idea of where they came from. If you look at the networks which generalize better than others, they usually have smaller weights. What does it mean? It means that the probability, the distribution probability of networks which generalize better is closer to zero because it's small. How do I write a probability distribution which pushes my weights to be equal to zero? One possible solution is to say that on average weights are equal to zero, plus or minus, let's say, some standard deviation. So one possible way, and here I come to one of the questions, which is, can you make an example of such a prior? Well, the prior that we could think about is that our weights are small, which means they are more or less zero plus minus something. I mean, if this something is very, very small, probably we are setting the weights all to zero. And this means that our network it's very rigid, it's not really flexible. If this plus minus something is very big, your network will be very, very flexible. So you can use this parameter, which is the variance of the weights, to say make it very, 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 very regularized when sigma is small, make it very flexible when sigma is very big. Okay, let's see what does it mean this in practice. So I just said that we want to fit the weights as the maximum a posteriori of my weight given the data. We have seen that the maximum a posteriori of the weight by using the Bayesian theorem writes as the probability of this term that I am upon now, which is the likelihood of the data, that is basically as we were doing before, times the probability of my weights. Now, if we are in let's say regression case, basically the probability of my data is the usual Gaussian distribution where you have some noise. Sigma square is the noise in the data, and on the top you have the difference between the observed target values and the neural network output. So the part on the left, let me see if I can highlight it somehow. So the part on the left, which is this part, is the usual likelihood. So based on your, let's say, usual likelihood, you are estimating the probability of the data given the weights. But now we are saying something more. We would like also to take into account the probability of the weights. Now, if the weights, remember the previous slide, if the weights are distributed as a Gaussian function with zero mean, the total probability, which is the probability of the specific weights of a neural network, can be written this way. Basically, Q is the number of weights in your model. So basically, Q is saying that you are considering the full joint distribution of your weights. Well, let's assume that the weights are independent one from each other, so we can write the joint distribution of your weights, which is your prior, as the product of the probability of each weight. I will point you to observe that here you have the noise in the data, which is this sigma, that unfortunately you don't know, and the let's say prior on how these weights are distributed, whether they should be very, very, very close to zero or whether they can take values everywhere. Okay, we move from the argmax of these two probabilities to the arg mean of the sums. How do we do this? Basically, we take the logarithm. So the logarithm of the product is the sum of the logarithm. The logarithm of this term is basically e to the minus tn and so on. So this is basically the logarithm plus one constant of this term, e to the minus, to which I have changed the minus, which has made the maximum to become a minimum. And in this case, taking the logarithm of this basically has a constant term, which is the logarithm of this constant term, minus this term. Since I'm turning an argmax into an argmin, I just change the sign. So basically, the sum of the logarithms become the sum of all wq squared divided to sigma squared w. Okay. As you see, differently from what we got from the maximum likelihood estimation, now this sigma square does not cancel out. In the sense that to cancel out this sigma square, you have to multiply everything by 2 sigma square. Okay, let's multiply everything by 2 sigma square, and we get this. So what is gamma? Well, gamma, let me highlight it in a different color. Let's see which, purple, hopefully it will. So basically, gamma, no, horrible, sorry for that. Let's take a color which is less funky. Let's take this. Gamma is the ratio of 2 sigma square divided by 2 sigma square w, where sigma square w is your assumption on the basically variance on the flexibility of the model, sigma square is the variance of the noise on top of the model. So basically, the first term is the same of before. So this term tells you how much you should fit the data. So this is a fitting term, and it's related to this part. And the second term is the regularization term. It is telling you how much you should minimize the weight. So the more you put weight on the fitting, the more you try to fit the data. The more you try to regularize this, the more you will get a very rigid model. That means that it will not fit. The trade-off between how much you can fit the let's say the data with respect to regularize the model is given by one number, which is this gamma, which is the trade-off between the fitting and the regularization. Okay, now I have a couple of questions which I've been ignoring, but just because now that I've finished, it's easier to answer the first one. But in the end, this approach is the same of ridge regression. Yes, exactly. This is exactly the idea of ridge regression. Ridge regression minimizes the sum of the parameters of the linear regression. What about lasso, for instance? Well, lasso, for people that do not know what lasso is, instead of minimizing the sum of the squares of the parameter, minimizes the sum of the absolute values. It can be proved that with lasso, the distribution of the weights is assumed to be hyper-exponential, so you try to squeeze to zero even more the weights. Okay. It is reasonable to assume that the weights are independent from each other, given that during training the evolution of their value is strictly dependent on each other. No, there is a clear co-adaptation between the weights. Indeed, this is an approximation of the joint probability of the weights. The problem is that if you don't assume this, you cannot solve the problem so easily as I'm writing here, which is at the end is a way to easily regularize this. And by the way, people have been using ridge regression without complaining too much about this co-adaptation. How to deal with co-adaptation of weights, I will talk in half an hour, don't worry. Okay, people don't get this, okay. So, this is very... So, let's look at this argmin, this. Now we multiply everything by 2 sigma square. Sorry for writing this way, but with the mouse is impossible. Now, if you multiply all the terms by 2 sigma square, what happens is that now I can use the purple. It means that this cancel. And here you have 2 sigma square divided by 2 sigma square W. The 2 cancel here. So basically, gamma is nothing but 2 sigma square divided by 2 sigma square weights. 2 sigma square is the noise on the data, which you don't know. And sigma square W is your prior on the, let's say, spread of the weight or on the amount of, of regularization that you have to put in the data. Now, you don't know the noise, you don't know the prior. I mean, instead of having to guess two parameters, it's better to have only one, which makes easy to also interpret this formula. If gamma is low, basically you are just fitting and you go back to the maximum likelihood estimation. If gamma is very high, you are highly regularizing, so basically you are ignoring the data and you are just pushing the weight to zero. Okay. Um, okay, 2 sigma. Okay, we have answer to this. Another question. The probability of the data is not present on the denominator because there's nothing to maximize in that term, right? Correct. So you don't want exactly the a posteriori distribution. You want to find the maximum of the a posteriori distribution. So the probability of the data that comes from the Bayes theorem, basically, it's useless because it's just a constant term. People working in Bayesian statistics, right now they would say, haha, life is easy that way, because the evidence, which is the probability of the data, is the most difficult part to estimate in Bayesian statistics. But I'm not doing here Bayesian statistics. I'm just finding a maximum a posteriori estimator. So yes, life it's way easier that way. So another question is the distribution of the weight is given by us, right? Correct. And by that, it follows this error function. If you don't like the Gaussian, then you have to find another distribution which makes this computation easy. And there are not that many, I can assure you. So usually people tend to use a nice distribution which makes the posterior calculation simpler. So that's why we decided for the Gaussian. But then the idea is that what I want to do is that I want to concentrate my weights close to zero. So in a sense, any distribution which has the most of the mass around zero works, and the Gaussian is one of these. If it has a lot of mass close to zero, might change the rules, and you can get the lasso solution. Um, okay, one question is it's very important in a sense that it says I named this as regularization. At the end, also early stopping wants to do the same. That is prevents overfitting. Can we call early stopping as a regularization because it does the same? The same means it prevents overfitting. In a sense, yes, but it is stretching a little bit the term. When you say model regularization, usually means to write explicitly an added cost term on the parameters of the models. But if you interpret regularization as improving generalization, yes, you can think about that. What is the meaning of probability of data? Okay, if we have the data, we know them. Okay, what is the probability of the data? If we have the data, we know them exactly. Well, not really, in a sense that you, uh, in a sense, you would like to compute the integral over all possible parameters of the data. So you have to marginalize out the data. So basically, it is useless. When I was referring to Bayesian statistics, it means that you have to compute an integral at that point to write this distribution in closed form. And I mean, it is not always easy to do that. Okay, okay, okay. Why this procedure limits overfitting? Okay, that's a very good question. And it's related to the observation. Let me go back to the previous slide, to this observation, which is, let me highlight it. It has been observed that the small weight improve generalization. So in a sense, you can think about this. Weights, they represent how much your output changes with a small change in the input. So basically, if you have small weights, you have a small gain. If you have big weights, you have a big change in the output. So the smoothness of the model is related to the, let's say, domain of the weights. Extremely smoothed models, all near to zero, they basically have an output which is very, very close to zero. Models which are not smoothed at all, so you can have any possible random weights, they can change very abruptly. And so you can, here it comes the sense of regularization. Why regular? Regular means regular in shape, which means smooth. So basically, what this is doing, it is smoothing your model. Basically, what you are defining again is just another loss function. So we see that the task for a neural network is defined in the loss function. If you have the mean square error, we are saying fit the data as most as possible under a regression task. If we add this term, we are saying fit the data, but keep the model simple. And if we put cross entropy here plus some regularization, we are going to say the same. Fit the data in classification context, but limit the overfitting. So playing with the loss function is very important. The problem here is that you have to set this gamma parameter. So sorry, I wanted to select the laser pointer. So how do we select the gamma parameter? Let's see, I will answer a couple of questions. Okay. Now, the question is, we can use lasso to do feature selection, removing features with a weight near to zero. Could we do something similar also with neural network, maybe removing neurons with all weight near? Yes, it is correct. If you, this is a sort of, so if you remove, I didn't get exactly the question, but you will get a correct answer in a few minutes. Wait a second. So if you write lasso here, for people that don't know what is lasso, it is instead of using the let's use this color. Instead of using the sum of squared weight, it using the sum of the norm, the module of the weights. Sorry, this thing. I haven't bought yet the graphic table, but don't worry, I will get a tablet for doing this kind of thing. So if instead of minimizing this term, which is the square of the weights, you minimize the sum of the absolute values, basically you are pushing the weights very, very, very close to zero. And that's why you will get feature selection. Okay. Now, okay. Okay, I see that someone is pushing to wait the end for this question. Okay, okay. I will. To be honest, I'm answering questions which I think are related. The questions which are not related, I'm skipping. Don't worry. So this is important because you will see this later on um, with Giacomo. So he will talk about L2 and L1 regularization. So basically, this the sum of the square value is called L2 because you have a norm L2 regularization. The absolute value is called L1 regularization. Okay, what I was saying before is there is still a missing piece, which is, let me take the pointer, which is this. How do we set the gamma value? To set the gamma value, we should set the gamma value for which we do not regularize too much, and we don't regularize too little. So we have to find a trade-off for deciding about regularization. So we can imagine that gamma is a hyperparameter because is a parameter that I have to set before starting training in order to find the right balance between fitting the model and performing regularization. So how do we select gamma? We treat gamma, and in general, we treat all the hyperparameter at the same way as an hyperparameter. So we use, again, cross-validation to select the proper gamma. So what we do is we split the data in training and validation. So we hide some data. We minimize the error, the weight decay error for different values of gamma. And we evaluate this model by looking at the prediction error on some validation set. So let's assume I start with gamma equals 0.1. These numbers are random in a sense that you might get benefit already with 0.0001. So, I mean, you have to test from 0 possibly to infinite. I'm saying positive because having an infinite regularization doesn't make sense. So you train with gamma equal to 0.1. You test on the validation and you get this validation error. Then you test with gamma equal to 1. Then you test with gamma equal to 5. And then you go on, I don't know, gamma equal to 100. So what you expect is that differently from the effect on early stopping, the more you increase the regularization, at a certain point you reach a level where all the weights are 0 and basically you are predicting the sum of the square values of the targets because you have regularized so much that all the weights are 0. So basically G is always equal to 0. So that's why it has this shape. Basically, you will never look at this shape. You will only look at the first part in general, and usually the weights are the gamma values are way much more smaller. Well, you will probably never have gamma which is bigger than 0.1, 0.2. So, I mean, don't don't look at this number as a reference. Just take these numbers as an idea that you have to start from 0 and increase gamma. And usually what you do, you start with the number, then you take 10 times, then 10 times. You see that you already start in the wrong area. Then you split the interval and then you refine the search. At a certain point, you will find one gamma star which has in your let's say, experiment the best validation error. Now you can pull all the data together. After all, the idea of using regularization is to use all the data. And now you minimize the error function, which is the weight decay error function, which has the right amount of generalization. What does it mean, the right amount of generalization? It means that you can train on the training set without early stopping, and it will not overfit. Indeed, all these experiments have been trained on a regularized model without early stopping, because we want to find the right amount of regularization such that without early stopping we get a good result. Then we put back all the data and we figure out what is the best set of weight using all the data. Putting back all the data, now I'm giving you a suggestion that might be handy later on during the challenge, is what made some of your colleagues get better performance. So they were using early stopping, they were getting a certain result. The problem is that they were training with not billions of records, that they were having a few hundreds of records, and setting apart, I don't know, 1/5 or 20% for validation was removing the data. So they decided to do this trick, which is they selected the right amount of regularization and then they used all the data. Let me go back to the idea. Can we do the same with early stopping? More or less, yes, in the sense that we could perform early stopping. Let me go back a little bit. We can go back to this point. So we train until the validation set error stops decreasing, and we decide that this is our best model. What is our best model? Is the model which has a certain number of neurons and which we train for k early stopping epochs. At this point, if you are desperate and you want to win a competition at any in any case, what you do, you say, okay, let's assume this k is our regularization factor, in the sense that at k epoch I'm overfitting. Let's put all the data together. Let's train until k. It might not be the optimal one, but I will give this a try for my model. This is not something I suggest to do in real life, because real life is, let's say, is not about winning with the model, but in some cases it gives a better performance. So early stopping, my suggestion is leave it as is. But and if you want to use all the data, use a form of regularization like weight decay, which basically penalizes models which are complex more than what you need. To select the right parameter of weight decay, you have to make different trials, and because of that, you will find what is the best case. In this case, you can train on this. Yesterday, I assume you have seen this already with Francesco when discussing the fact that you can put a regularization term on the weights. Indeed, this weight decay can be applied on all the weights, like in this example, or you can apply the regularization on each single layer. So you might decide that you only regularize this layer while the other you keep as is, and basically when you perform gradient descent, the gradient descent will take into account this summation only for the weights for which you have uh, stated that you want them to be regularized. Okay, question about we first choose the gamma and then train, but how do we initialize the weights? Weights are always initialized randomly. Every time you start a new training, you initialize the weights randomly. There are smarter ways of initializing the weights, but I will discuss this after the break. Other questions? Uh, in gamma, tuning in each epoch is used. No, no, no. In gamma, you split only once and then you test for different possible gammas. You don't split every round. When we say put data together, the test portion is always out. Yes, test, it does not exist for us. Test is in the hand of our boss, and it will be used only to decide how much to pay us. But it's not too expensive. Yes, the training and designing and hyperparameter tuning of a neural model is very expensive. Uh, a few years ago, for 3, 4 years ago, I invited young Goodfellow before he became famous and wrote the book on deep learning to give a seminar about deep learning to my student. Uh, to make a long story short, he was in Italy because his girlfriend is from Bergamo, just to give you a hint, and or at least it was she was from Bergamo at that time. Basically, he said that at Google, what they do, they launch on 200, 300 different server, 300 different model at the time. Uh, the day after, you have 350 models, you pick the one which works best, and you throw all the others. Now, if you do the math, it means that to select one model, they have used 350 days of computation. So clearly, not everyone can do that. So what you do usually, you subsample the space of possible parameters. You don't try all of them. That's the point. Okay, so okay, let's take a break now. So we can start with the third and last technique for regularization. And then I would like to talk about the two more things today, which are network weights initialization and better activation function. So I will stop now the recording. I'm pausing it. I'm not stopping it. 1 hour and 14 minutes sharp. Let's start at 6 sharp, so we can finish by 7:15. Okay, see you later. Bye bye. Okay, here we go. Can you hear me? Okay, cool. So, um, before I start, I resume the recording. Don't worry, I will not forget. At the beginning of the lecture, there was a question in the chat that I noted down to answer, which is about the change of groups. I posted a note in the on the chat, sorry, on the website, saying that Presidenza has approved the change of group for the people that asked me via the form. They were 33 people, which actually they are 33, but basically 10 move in one direction and 10 move in the other direction. So basically, the real number that will change is almost 20 or something. So basically, what I'm going to do is putting on the a link, sorry, a document on the course website in which I'm saying which is moving from group 1 to group B and vice versa. Sorry, group 1 to group 2 and vice versa. So if you have filed the form for the change of class because you have overlap of classes and timing and so on, from next week you have to you can start coming to the other group. The only situation that I find critical is the second group, because the class is smaller. So I will keep an eye on whether we can fit legally, I would say, in all the spots. So while moving from the second group to the first, which is the first of the two lectures on Wednesday, this I feel it's safe. The other way around, we are at the right number in the class. So that's something we have to be careful about. But besides that, it has been approved. It took a while because so far everyone was asking to change one person, two person, and so on. And my course was the first ones asking to move 30 people, and they had to understand how to do that. So that will appear. I haven't put it already on the course website because I have to process your forms in order not to publish your codice persona, because I'm not allowed to post on the course website your codice persona. So I will use your matricola, and I have to do this, but I will do it, and everything should be fine. Okay, so I'm resuming the recording now after the break, and I would like to continue on different techniques for improving the generalization capability of a neural network, that is to overcome overfitting. So the idea is that finding the right balance between model complexity and overfitting is not always easy. And so there are techniques. My favorite, as I said, is early stopping, where you oversize the model and then you rely on the early stopping not to overfit. There are techniques which they don't want to waste data, so they add some regularization. Another technique is called dropout. Dropout is a technique relatively recent. What do I mean? It means that it doesn't have a classical statistical counterpart. So if early stopping has the, let's say, the ridge regression counterpart, stochastic regularization is more tricky. So if you see a network, we have seen that to regularize the network, one thing that you could do is to set the weights to 0. This goes under the assumption, as one of your colleague was saying, that weights are independent. Actually, they are not. What does it mean? It means that sometimes they tend to co-adapt, and that is one neuron, one weight will set to a certain output because another neuron has set to another. And this is something that might prevent a proper learning. So to reduce this fact that one neuron tends to optimize the weight with respect to what another neuron has done, dropout was invented. How does it work? Well, when you train this network, you backpropagate and you update each single line in the network. So backpropagation, what it does, it basically switches off one hidden node, one neuron randomly with a certain probability. So basically what you have is that for each layer you have a mask. This mask is given by a set of bits. You sample these bits from a binary distribution, a Bernoulli with a certain probability, and then what you do, you switch off with this mask the neurons that have a 0 or a 1, depends on how you interpret that, in this layer. Then you do the same here, then you do the same here. So switching off this neuron, it means that all the weights all the arrows going out of these neurons are basically equal to 0. It means that this neuron in the output will have one input less, or on average a certain percentage of link less, and it will have to learn a model which works even with less parameters. Now, the interesting thing is that you do this at any epoch. So what you do is basically you switch off the links, you do an update, then you switch off different links, you do another update, then you switch off other links, you do another update, you switch off other link. By doing this way, let's go a little bit back to the original model. What you do is that instead of having a huge model like this, monolithic, in which any weight has been trained somehow based on the values of all the others, at the end, when you have trained this model by switching these nodes, then other, then other, then other, the final model that you get by switching on all the nodes can be interpreted as the sum of many other models, the sum or the average of many other models which have been trained independently one from the other. So basically, what you do is at each, let's say, iteration or each batch or each, what you do, you switch off a certain amount of neurons. So this mask is just a mathematical trick to select randomly the neurons not to use. And basically, the way you do it is by saying, okay, the output, you see here the formula, the output of a layer is the weighted sum of the output of the previous layers times this mask. So if this mask has a 1, you consider the output of the previous layer. If this mask has a 0, basically all the connection of this layer, of this, let's say, neuron here that I'm pointing at, basically they don't enter in the following layer. So basically this mask is the mathematical way of saying switch off randomly some of the neurons. Now, this mask can be activated by layer by layer. So you can decide to mask this layer while you keep all the others layer unchanged. Or, like in this case, you can decide to apply this dropout mask to all the layer. If you haven't seen this already with Francesco, but you might have, what you do is basically saying, okay, each layer of the original model here, just a second, then I'm going back to the original model. So for instance, let's assume that we take this layer, one second, select with here. So let's assume that I take this layer here, and I decide to apply dropout to this layer. So as you decide to use regularization on a per layer basis, you can use dropout on one single layer. It means that you add a dropout layer to the layer that I have highlighted here, and this dropout layer, it works like a mask, which means that it switches off the output of this layer and at the same time prevents to update the weights of this layer. So it really switches off this neuron, like removing the neurons from the network. So let's say that you have this mask on the green layer. At the next step, basically all the connection of the, sorry, I went too far, all the connection of that neuron which is in black basically is like they were not exist. What does it mean? It means that the model you are training is a simplified model. You see that this model, which is right now masked, has a less connection, so is a weaker model. When you put everything together at the end, basically what you have is that you have trained on each mini batch a different model, because it is slightly different as a model. And at the end, when you use all the neurons, it's like putting together all these methods. So basically, what you get is an ensemble method. What does it mean? The final model is the mix of a lot of smaller models that you have trained during the training phase by switching one after the other these neurons. So basically, you have to decide when you design a network on which of the layer you want to apply your dropout, which is this masking effect, and basically you improve the generalization capability. Where does this improvement comes from? It comes from the fact that you are obtaining a model as the average of many simpler models. This is called, in a sense, begging. What you're doing, you are performing begging on the model, implicit begging. Let's see a couple of questions. Every time you switch, yes, you decrease the power of the model. At the end, you have a model which is the mix of many simpler models. And this is the base for improving generalization. The mask is a Bernoulli distribution. Yes, it was there. How do we decide in which layer to apply the opt-out? How do we decide? Trial and error. Which layer to, let's say, add dropout is again a hyperparameter. So you have to make tests, validate the tests on the validation test. It means that you will have to use again cross-validation to select the model. So model selection in neural network means also to select to which and how many layers apply dropout. It is not automatic that adding dropout will help, because basically it might end up that you just are not able to learn the data with dropout. And another hyperparameter is the probability of switching out the neurons. The higher the probability, the more intense is the effect of regularization. Okay. Why Bernoulli distribution? Because they are either 0 and 1, and you want to extract 0 and 1 from for those things. And I mean, if you want to select 0 and 1, you draw a coin and you select 0 1. Okay, so other questions? Another question, since we are training Witter models and combining them isn't like boosting, not really. In boosting, you reweight well, yes, you reweight the samples. In this case, you are also using different batches. So it's both of them. You change model and you change data set at each step. So basically you are putting all together. So you get both the effect. Okay. Now, if there are no other questions, okay. Which one is the best? So which one should I use? Well, again, the best is the one that gives you the better result. So why basically you should prefer early stopping with respect to ADK with respect to dropout. You have to do model search. So basically you have to test many models, and you have to have a sound methodology to select one model with respect to the other. And the sound methodology is called cross-validation, which means to set aside some data that you use not for training, but to decide which of the model is the best in this context. Okay. The final combination. So the idea is that how do you perform the averaging? Well, the dropout. So this switch on and switch off is performed at the training time. When you use the model, you always keep all the neurons. It means that basically you are mixing all the models because all the neurons are active. Okay. How we can say that when we mix them all, we can get something useful? Well, we have trained basically already them all, because one piece at the time of the network on average has been trained, and on average it has been trained with all the others. So every neuron, when it was switched on, was observing a different subset of other neurons. So that's how dropout work. Now, does it work always? No, there are situations where a little bit of dropout helps. Other situations where you don't see any difference in using the dropout or not using the dropout. So early stopping, weight decay, and dropout are the most famous techniques for limiting overfitting. So a question, how do we select L2 regularization? Via validation set, correct. Everything is done via validation set. Once you have selected the right combination of parameters, you can basically put all the data together, train, and that's it, finished. But I mean, otherwise, you select the model that you have trained without even caring, and you select that model, and that's your final model. Or in general, I suggest to go for simple things. Start with early stopping, see how it works. Select the complexity of the model, always using early stopping. At some point, you might decide by using early stopping, to remove early stopping, but keeping the validation set, what would be the right regularization. Then you can test whether using dropout helps or not. And then when you have done everything together, you put the data, you train the last model with all the parameter set. But my suggestion in general is to start with early stopping, which is the easiest model to implement. Okay. Why shutting down neurons at each mini batch and not each epoch is one of the possible implementation. I mean, there are different implementation. I don't want to enter what is the TensorFlow 2 implementation. If you're curious, you're lucky, because TensorFlow 2 is open source, so you can enter in the library and check whether it does per epoch, per, or it might be that it has a parameter to tell you whether you want to do it per epoch, per mini batch, per something. One practical reason to do it per mini batch is because mini batch are done in parallel. So you can update all the weights in a mini batch in one shot, because TensorFlow is parallelized by mini batch, and by doing this, you are able to do it efficiently because you keep the model fixed, you update, and that's it. So basically, it is more an optimization thing. Okay, so these are the three most used techniques for improving generalization. To be honest, there are other, let's say, tricks to improve model generalization in a sense. So, for instance, data augmentation is one trick to improve the model generalization, but many of these you will see later on. So it makes no sense to talk about data augmentation today. If you check in the schedule, there is one lecture by Giacomo Boracchi on training with data scarcity, talking about convolutional neural network, and he will discuss about this topic. Okay. So I would like to stop now talking about generalization and overfitting, because I need to finish two topics that are very simple, but they need to be faced today. One is which which activation function to use. Now, so far, I have discussed the use of sigmoid and hyperbolic tangent as an activation function. And I have been supported by the fact that there is the universal approximation theorem in saying that this is a good thing to do. But the sigmoid and the hyperbolic tangent, they have some problem. So first of all, if they have a too big input, they tend to saturate. And what does it mean that they tend to saturate? Tend to saturate means that you basically have zero gradient here. Why is a problem? It is a problem because if you started from a wrong initialization, that is, you started from the neuron working in that saturated region, basically what you get is that you will take forever to go down the gradient and move on the other side to correct the weights. So basically, saturated functions are usually not good because they have zero gradient, so training is more difficult. Second issue with sigmoid and hyperbolic tangents is this. If you check here, the back propagation, what it has the derivative here of the activation function through all the layer that you are traversing. If you remember, we have seen that with the properties of composed function, you can, let's say, easily compute the backpropagation formula by concatenating the gradients, by multiplying the gradients of the traversed neurons and of the error function, which is, let me highlight it. So this is the error function. You should be easy. It should be easy to recognize, and the weights, which are these, of the traversed layers. Now the problem is this multiplication. Why? Because when you multiply numbers, if these numbers are, let's say, less than 1, the result can become very, very, very small. In particular, if you look at the derivative of the sigmoid and the hyperbolic tangent, the maximum of the derivative is here in the origin. The maximum of the derivative is basically 0.5. I never remember whether it is in the hyperbolic tangent or sigmoid, but let's say the derivative, it's everywhere less than 1. So when you compute the back propagation, you multiply 0.1, for instance, times 0.1, which means it becomes 0.01. If you have many, many layers, you are multiplying many, many numbers which are less than 1. So it means that far away from the output, the gradient becomes 0. This is called vanishing gradient. So the vanishing gradient is the effect of multiplying many, many times the numbers which are less than 1, and so you get a gradient which is basically 0. Since you start from a random initialization, the earlier input, they don't get corrected by the gradient. So basically, if you have a deep network, it means a very, very, let's say, long or huge concatenation of layers, this doesn't learn. This is a problem, clearly, because you start from a random initialization, you basically don't train the network. This is well known in recurrent neural network. We will come back to this, don't worry, later on, and I will show you the mathematical, let's say, formulation of this problem. But it also exists in a very deep network, and it is also why in the 90s they did not dare to have many layers, because with many layers they were not training. Because if you start with, I don't know, 10 layers, you get 10 to the minus 10 gradient, which means zero gradient. So basically, you don't get, sorry, yes, 10 to the, yeah, minus 10 as a gradient, which means a zero gradient. So even with the 3, 4, 5 layers, you cannot train because of this effect. Okay, can you increase the learning rate? How much? 15,000? I mean, when you have 10 to the minus 5, you get 10 to the minus 5. If you add another layer, you have to multiply. This will imply to have a different learning rate for each layer. Yes, it can be done, actually is correct, but basically you cannot solve it easily by playing with the learning rate. Also because really the learning rate should be adapted online to the gradients, and still if for instance you have 152 layers like the ResNet, the gradient is 1 to the minus 100, 150 in the first, when it reaches the beginning. So you can imagine that it is not going to work. So the solution is not in increasing the learning rate, is in changing the activation function. Here it comes, the so-called rectified linear unit. The rectified linear unit is a nonlinear function. You can tell it immediately, which is obtained by the sequence of the two lines. So this is this. By doing this, you get first of all a nonlinear function. Second, what we get is the fact that the gradient is either 0 or 1. And gradient equal to 1 is very nice, because if you multiply 1 by 1, so the gradient here is 1, and the gradient here, where it is 0. Forget for a moment about 0. Let's look at 1. The nice thing is the fact that basically you multiply a lot of times 1, and this remains constant. So you can have a constant learning rate. You can have a learning which goes through the beginning of the network. So basically, what we get by using this ReLU activation function is that we can have the gradient pass through even large network. Now you see why a few lectures ago I said let's keep using sigmoid and hyperbolic tangents for the hidden layers. What we will see later on is the fact that nowadays in practice we use rectified linear unit in the hidden layers. And the reason is exactly this. it's easier to train the network. The gradient can pass through many layers, and because of this, you are able to train the network. The universal approximation theorem, as originally written by the author, does not work anymore, but still we have other theorems that prove that even though the function is not an S function, but is, let's say, piecewise linear function, it can approximate anything. So instead of having let's say, sigmoidal or hyperbolic tangent based approximator, you have a piecewise linear approximator, and you solve the problem of vanishing gradient, at least partially, in the sense that there are issues and advantages. First of all, if you use the rectified linear unit, is way faster than using, I don't know, hyperbolic tangent and sigmoid. While, because computing the derivative is easy, you compute it with an if. If the input is positive, derivative equal to 1. If the input is negative, derivative is equal to 0. So you see that from a computational perspective, it is way faster. Second, it has sparse activation, in the sense that only part of the activation unit will have a positive output. Why? Because some of them, I cannot say how many of them, but a certain number will have a zero activation function. If they are zero, it means that they are switched off. If they are switched off, the model is more fast to compute, first. Second, it has less parameters, and so it is less flexible. So basically, it helps also in generalization. Efficient gradient propagation and efficient computation of the gradient. So it has been observed that with the rectified linear unit, training is faster and it works better. There is an issue of it is a scale invariant, in the sense that you can basically multiply and post multiply. So this is only for numerical reason. This is useful. Sorry, I did. Okay, sorry, I was missing this. There is also this advantage where you have scale invariance. So basically, you can do computational tricks and you can do other nice things on this effect. These are the advantages. Main first advantage is the fact that we can train bigger and bigger networks and more depth. First advantage. Second, it is faster to compute, and it is, let's say, more efficient at inference time. Okay. Question: are we losing too much information about the function? No, basically we don't have we don't lose enough information, in the sense that yes, the gradient is always either 0 or -1, but basically it has been proved that you only need to know whether you should go left or right. Indeed, there are implementation of training algorithm which they don't compute the gradient, they just compute the sign of the gradient. And then they use either an adaptive step or they just use the learning rate. So you don't need more of this. Okay. What about, so another question here. Sorry. What about the disadvantages? I mean, there are also some disadvantages in the rectified linear unit. It's not that it is the solution of everything. You should always, always, always consider that there is no holy grail. I mean, if you are gaining on one side, you are losing on another side. I mean, otherwise, you would have not been engineers. I mean, that's the point, and you should apply this approach uh, in all cases. So first, let's call it problem is that it's not differentiable in zero, which in mathematical terms is a set with probability zero. I mean, 1 point on the real line, it's not a problem. So this is a problem for a mathematician. I would say that it is not a problem from an engineer. An engineer say, okay, if I end up with exact zero, which has a probability equal to zero, I will set the gradient to 1 or to 0 with equal probability. I don't care, because I mean, this is not really a big issue. Another, it is not differently from the hyperbolic tangent, it is not centered in zero. So what does it mean? It means that if you need an output which has numbers which are both positive and negative, you cannot use the ReLU as output. Who cares? Again, this is not a problem, because basically, if you want to output between 0 and minus infinite and plus infinite, you put there a linear activation unit. You don't need. Indeed, these are only potential disadvantages. This should be disadvantages. Another issue is related to the fact that it is unbounded. What does it mean? It means that it is not saturating. So in some cases, the output can get very, very, very big, especially during training, if numbers are not well behaved. That's correct, especially if you have huge gradients, you might have problems. There are techniques to limit this. One is called gradient clipping. What does it mean? It means that if you observe that during your training the gradient is getting big and big and big, you decide that at most your gradient at each step can be applied by a certain limit. The real problem of ReLU is the so-called dying neurons. Well, what does it mean? I mean, a neuron which ends up to have a negative output here, a negative input is set to 0. So the output is set to 0. Not only this, but also the gradient is set to 0. What does it mean? It means that if a neuron by mistake is working in this area and you would like to move this neuron somewhere else, this becomes impossible. So what happens is that during training, it might happen that some neurons switch off and you are not anymore able to switch them on again. It means that by mistake, for instance, or by because you just initialized wrongly the weights, you are losing some of the computational power of your network. There are little solutions to this. One of these, and the problem is that this decreases the model capacity. So when you, by mistake, switch off a neuron, what you get is that this neuron gets removed from the the network, and because of this, you lose network capacity. It happens especially if you have a high learning rate. So by chance, you let's say you are on this side, you want to move here, you make a huge jump and you go on the wrong side, and because of this, you switch off the neuron. Possible solution: ignore the problem. This is somehow still a valid solution. There are alternative error function. One is the leaky ReLU. So what does it mean, leaky? It means that the gradient for negative values is not exactly zero. And basically, if it's not exactly zero, so in this case it is 0.01, if you end up on the wrong side of the neuron, what you get is that you will need some time, but you will be able to get unstuck for that condition. Okay. To fix also the zero, the non-differentiable point in zero, also this exponential exponential linear unit has been proposed, where this piece of the model is part of an exponential function, and in this case you are able to escape the dying neuron problem first, and you don't have the non-differentiability in zero. Personally, I have tried to use this exponentially linear unit, but I didn't find particularly benefit out of using it. From time to time, we try to see if the leaky ReLU works better, but is a sort of a minor improvement with respect of using standard rectified linear unit. What might turn out is that when you use leaky rectified linear unit, you will have less dying neuron, because at that point you are being able to rescue the neurons that you have unnecessarily killed. Okay. Well, the derivative of the exponential will be similar to sigmoid. Well, I mean, not really. Just do the derivative of this, and that's the derivative of the leaky ReLU. Leaky ReLU. It is basically alpha times E of x. That's the basically the derivative of this. Okay. Questions, mixed questions. I will answer the question at the end, because I want to really finish the second, let's say, small hint that I need to give before you can go and play with all the neural networks that you want. Weight initialization. So far, we have discussed activation function, model sizing, how to prevent overfitting, what are the techniques to prevent overfitting, how to fine-tune the parameter which prevent overfitting, that is by doing cross-validation. Now, one of the things that affects the gradient descent is weight initialization, because I already said that if you initialize the neuron in the wrong place, it will take long time to change because of the derivative, or if you initialize the ReLU function on the wrong side, you will end up by killing them on the first stage. So first thing, if you think initializing to zero your weights, this is not going to work. Indeed, if you remember in the formula of the backpropagation, you multiply by the weights. And if you multiply everything by 0, this is not going to work. So unfortunately, this is something you shouldn't do. Big number, bad idea. A big number, bad idea, because you have big gradients, which are not good. And second, if you have sigmoid and hyperbolic tangents around, if you do, if the weight end up to be on the wrong side, what happens is that it will take a long time to correct the weights, because the gradient on the saturated area are basically flat, so useless. So no zeros, no big number. Small numbers. So another option is to initialize with Gaussian distribution with a variance, let's say, very small. This is the classical default or classical easy way. So usually, especially when the network are very small, this works reasonably bad. Works reasonably good. Why it might be a problem for deep neural network? So why, if you try to initialize with very small weights the network, you might end up with problem in deep network. Again, because you should always think what's happening. You're doing gradient descent. You're applying the backpropagation formula. The backpropagation formula is the multiplication of weights of the link traversed by the backward pass times the derivatives of the functions that have been traversed. We have fixed the issue of having zero gradient for the function. If we set close to zero the weights, we get a vanishing gradient due to this weight with very deep network. So if you are not working with a very deep network, is not a problem. If you are working with very deep network, this might create issues. Okay, so when you have a very deep network, you should have different ways of initializing the weights. So when you have a very deep network, what you should do is to, let's say, make the weights not too small, not too big. Not too small because, as we have seen, the gradient shrinks every time it passes through each layer. If they are too big, the gradient explodes or grows every time it traverses the link, because we have seen that every time you traverse a link or a layer, you multiply the gradient by the weight of that layer. So what you should do is to have, let's say, more or less weights which preserve the magnitude of the gradient, not to have very big discontinuities between each layer. So in a sense, the signal more or less which exits or which enters each layer should have more or less the same range. Otherwise, if you multiply it every time you pass through a layer, or you shrink it every time you pass through a layer, you end up destroying the network or the gradient. So it should be unchanged. And this is the idea of Xavier initialization. So let's think about one neuron. This is the classical hidden neuron. And we know that the, let's say, activation function of a hidden neuron is given by the weighted sum of the input. If we assume that for the time being, let's keep it linear. So let's assume that it is with high component and linear. So the nonlinear case might be more complex, but let's take the linear. We can assume what is the range or the variance of the output of this neuron. What we would like is to have the output of this neuron not to become too big, not to become too small. So if we take each of these terms, this term will have a variance that is the variance is the variability of this term, which is due by the variance of the input times the variance of the weight plus the expected value of x squared times the variance of the weights plus the expected squared value of the weights times the variance plus the covariance between these two. So what I'm saying here is that if we assume that weights can have different values and input can have different values, if we want to keep the output of the neuron in a fixed range, we have to control the variability of its terms. Now let's assume that we have weights with mean equal to 0 and input with mean equal to 0. The formula for the variability of the terms in the output of the neurons simplifies like the variance of the weights times the variance of the input. Okay, so let me recall what we are trying to do. We are trying to figure out what should be the weight on average, not to have the gradient to shrink too much, not to have the gradient to become too big. If we assume that all the weights are independent and all the inputs are independent, we can compute the variability of the output of my neuron, which is how much it's likely that goes to 0, to plus infinite, or to minus infinite, as the variability, which is the variance of its elements. Since all its elements, they are distributed the same way, it is I times the variability of the weights times the variability of the input. So this is a constant term. This is a term which basically amplifies, the one that I'm highlighting in red now, amplifies the input. So basically, if we have, let me put that in red, I'm sorry for the color, it's not probably the best one. So if we compute how much is the variability of the output of the neuron, it is equal to the variability of the input, which is this one, times the red term. So basically, the activation function, the value, the sum of the input of a neuron is amplified by a quantity on average, which is I times the variance of the weights. What we said is that we don't want the weights to amplify too much the input, nor to shrink the input too much. Because if you amplify too much, the gradient might explode. If you shrink too much, the gradient might shrink too much. So what is the magic number which doesn't amplify and does not shrink? 1. So you would like to initialize the weights in such a way that this terms is more or less 1. If you initialize this term more or less equal to 1, what happens is that the gradient does not explode, the gradient does not shrink, and so you are able to go with the gradient on average through all the layers. All this reasoning was done by Xavier in a paper which suggested to initialize the weights of a neural network in such a way that the number of input times the variance of the weight should be equal to 1, which means that if you initialized the variance of the weights equal to 1 divided by the number of the input, this is true. So basically, Xavier proposes to initialize the weight of each neuron sampling from a Gaussian distribution with 0 mean and a number of and a variance which is inversely proportional to the number of input. I see someone is confused by I. I, if you see the previous formula, is the number of variables in input to the neuron. So basically, what you get is that you initialize the weight with a Gaussian distribution, which is something which is easy to compute, which has basically the variance equal to the number of input. At the same time, two other authors were doing the same computation, but from the output perspective, and they found out a similar formula which says that if you don't want to amplify too much the gradient, especially at the beginning of the training, you should initialize the weight by this term, which is n output, so the number of output of the neuron times the variance of the weights. This should be equal to 1. So Glorot and Benjo find out that the weights should be initialized by, let's say, a Gaussian, which has a variance which is 1 over the number of output. Xavier find out that they should be initialized to get a good result by the number of input, and at the end they decided to use a middle ground approach. So the Xavier initialization or Glorot initialization is this one. Which one is the winner? It doesn't really matter. I mean, these are very similar in numbers because it is not order of magnitude the difference between the number of input and number of output. The important thing is that you need to initialize each layer by considering how many neurons are coming before and after. There is another proposal which was done by he, which says, you know what, instead of using the previous formula, which uses a linear activation function, we use the neuron as a rectified linear unit. So if you rectify this neuron, you have to consider that only half on average of the neurons are active. So you have to correct this formula by adding a 2, because it is not true anymore that all the input are useful, because on average half of the input will be dying neuron, and so they will be useful. So, and the nice thing is that now, according to the he proposal, the original hypothesis that the output of the neuron, sorry, just a second, is a linear combination, now it works. This hypothesis now it works because for the neurons which are not dead, this is exactly the output. And so, to make a long story short, if you have a small neural network initialized with a Gaussian distribution with zero mean and a variance which is usually small, if you have a deep neural network using either Xavier initialization or the He initialization, usually performs better when you perform training. So basically you initialize this. If I'm not wrong, but I might be wrong, you can I'm sure you can specify in Keras the network initializer you prefer. You can select Glor, Xavier, or normal distribution or zero weights. I don't remember which one is the default. We should go on Keras and check which one is the default. Okay. Linear assumption seems too much, but that's it. Last comment, it takes really 5 minutes, then I will finish. So today I've tried to share with you more of the practical thing, how to stop overfitting, how to select the activation function, how to fine tune the parameters, how to initialize the weight. Let me give you another hyperparameter which is often used, which is the training algorithm. What we know now is that we can use backpropagation. We know perfectly how it works. We know that there are variations of the backpropagation. So here we see already two algorithm. One is gradient descent. The other one is gradient descent with momentum. There is a huge literature of algorithm for nonlinear function optimization. Some of them are useful, some of them are less useful, some of them are, let's say, very, let's say, strange in the implementation. I will give you one example. This is called the Nesterov accelerated gradient. So is a gradient descent which converge faster. It is similar to momentum, but it does it in two steps. So the first step, which we call half step, it applies the momentum. In the next step, it applies the gradient descent. And it alternates momentum, gradient descent, momentum, gradient descent. So what you get is, for instance, with the standard momentum, you have the blue version. With the brown and red, you have brown half step, and then you have the correction, which is the let's say this second part of the gradient. Then you have a half step, then the correction. So usually what happens is that these gradients tend to converge faster. As I said, there are lots of algorithm, plus there are some other effect where you try to adapt the learning rate. I will not discuss each of them. Actually, I will not discuss any of them. I want to just tell you that since the 90s, there are many algorithms to replace stochastic gradient descent. So if you use stochastic gradient descent in the code, you use exactly what we have been discussing in class. More recent algorithms like Adam, they keep memory of the gradient and try to adapt the learning rate to see if the gradient is decreasing, the gradient is increasing, or the gradient is oscillating. So the nice part of Adam is that you give an initial guess of the learning rate, then it adapts the learning rate at each iteration. Very similar other algorithm. The resilient backpropagation, which dates back to the 90s, is another algorithm that I really like, not because I'm old and reminds me the time when I was studying neural network, but it is nice because it only uses the sign. So resilient backpropagation doesn't care about how big is the gradient, it only decides in which direction to move. And this is one interesting idea. And then you can mix and match and do whatever you want. I will leave you with this last example, which is one example of how starting from the very same initial initialization, you might easily find the minimum. The minimum is where the star is, and the trajectory followed by different algorithm. You see that some of them reach the star way earlier than other. You see that all of them reach the star. You see that the slowest ever algorithm among these is the stochastic gradient descent. So I'm keeping saying to use stochastic gradient descent, but it is slow. On average, it is very, very slow. And what you do usually is you use other algorithm. As you see, AdaGrad or AdaDelta, Adam is not here, are the fastest because they really adapt the step of the algorithm based on the shape of the error function. Other algorithm like the stochastic gradient descent, the stochastic gradient descent with momentum, and the Nesterov, so the Nesterov is this purple one, can be slower than the original one. Okay, so no, I don't want to talk about this. These are what I have called the tip and tricks, but tip and tricks. But in practice, these are the things that you will have to test and use during your challenges. You will see that while doing some experience on this, you get some sensibility on how to size a model, but you will start relying more and more and more on cross-validation, in the sense that you will need to perform hyperparameter selection and tuning. Don't get obsessed about this. I mean, start with the model, make it working, try to understand where is the problem, and be very methodic in the design of a model. In the next lectures with Boracchi, you will see models which have been trained. You will see much more tricks on making these learning procedure more effective. For instance, you will see the trick of a shortcut connection. You might see the trick of residual blocks. I mean, you will see a lot of tricks to improve this. But what we have seen so far is the basics. And with this, you should be able to understand what you're doing and what is working, what is not. Okay, I would like to answer a few questions now. The learning rate, so just a second, I adjust message. So I will start from the end. So learning rate is changed starting from the first suggestion, depends on the algorithm. Usually what is done is that you start with the learning rate, and the more you train, the more you reduce the learning rate. In particular, this is another technique which is used a lot. What you do, at some point you reduce the learning rate. This is called learning rate scheduling, and I will explain why you want to do learning rate scheduling with this example. So let's assume you have a very high learning rate at the beginning. I will exaggerate this a little bit. Just a second. So let's assume you start from here, and then you jump here, and then you jump here, and then you jump here, sorry, and then you jump here, here, here. And basically you will never end up in the minimum, but you will be around the minimum because you're just jumping back and forth for a lower learning rate. If at a certain point you reduce the learning rate, what you see is that you will end up in the minimum. So changing the learning rate helps. When you are at convergence and you see that you cannot improve, you might have ended up in this condition. If you have ended up in this back and forth cycling on one side or the other of the valley of the error function, you might want to reduce the learning rate and the learning becomes more stable. Okay. I see the question on. Would weight regularization fix the dying ReLU issue? No, because the regularization, okay, in the sense that you will not change too much the regularization, the weight, and you will not kill it immediately. No, I think that this is so weight regularization basically shrinks the weight to zero. It means that they will be in the dangerous zone, in a sense. What makes the dying neuron to happen is those big jumps, because when you make big jumps, it's easy to traverse the zero. But again, don't worry. I mean, people are still surviving the presence of a dying neuron. It is a waste of computational power because you don't use them at that point. Okay, other questions? Uh-huh. Okay, using ReLU as activation function, can we implement the mask of dropout? No, they are different concepts. I mean, ReLU is an activation function. The fact that it dies from time to time is something that you have to accept. But this means that this doesn't mean that you cannot add the dropout after the rectified linear unit. Actually, this is done. I mean, ReLU is just a replacement of sigmoid and hyperbolic tangent to train deep neural networks and to make training faster. So that's the right way of looking at this. Could you repeat in which cases gradient vanishing may happen? Gradient vanishing, in a sense, happens always because you multiply numbers. If you multiply small numbers, you have vanishing gradient. If you are able to keep these numbers as close as possible to 1, then you can remove, as a matter of fact, some, let's say, let me rephrase. So you have vanishing gradient because you multiply the gradient. If this gradient is less than 1, this is a problem. If the gradient is equal to 1, this is not a problem. So the vanishing gradient happens if your gradient is less than 1. It happens every time you use a sigmoid and hyperbolic tangent through many layers. And this is why usually we suggest to use rectified linear unit which do not have this problem. Other questions? Okay. Okay, one more message. So could you repeat why x and sorry, this part? Let me go back. Just a second. Here. Okay. 1 second. Let me load this slide. So no, that was the previous one. So can you repeat why the input has variance? And so basically, what I'm trying to show here is how can I relate the weight initialization to the effect that this weight initialization has on the net. Weight initialization has an effect on the output of the neuron. The output of the neuron basically is amplified. Sorry, the output of the neuron depends on the input, which gets amplified by the weights. If you don't want to over amplify it and you don't want over, let's say, shrink it at the beginning, because if you shrink it at the beginning, you start with the vanishing gradient, you don't go anywhere. You need to initialize the network in a state which is reasonable. A state which is reasonable is a state where everything is close to one. And that's why we try to initialize things in such a way that you have gain which is more or less equal to 1. That's the idea behind this. Okay, let me go back if there are unanswered questions. Okay, no, the others I should have answered. Okay. For classification, the hidden layers have ReLU and the output sigmoid or tangent, hyperbolic tangents, correct. But if you have multi-class classification, the output should be softmax, not sigmoid. Okay. Okay. Okay, so I have also private messages that you don't see. They are nothing which is something to be scared about. I'm just saying to the person which is writing private messages to me, yes, I will take care of your messages after the lecture. Just a question. Well, no, I think that we run out of questions. Okay, if we run out of questions, as usual, I have to say, from time to time, I have students that have doubts when studying. They drop me an email. That's not a problem. I reply to students asking for doubts, try to clarify the thing. So an email like I didn't understand what is backpropagation is an email that I don't tend to answer to. I suggest to review the videos since I'm recording everything. But if there are very specific aspects that you don't understand, just drop me an email. It's not a problem. I mean, already every week I received 6 or 5, 6, 8 emails of doubts. Hope by after this message I will not increase too much the number of email with doubts, but there's no problem. With today, we don't see each other for a few weeks. According to the program, I don't remember if this is for 2 or 3 weeks. We will see each other after Boracchi has finished the part with about images, and he has and I will start talking about sequences, because so far we haven't taken time into account. Sometimes data and let's say data have a time or a sequence behavior of a sequential behavior, and because of this you have to take into account, but this will be in a few weeks from now, so not today. With this I'm closing. First of all, I'm closing the recording. Okay, stop recording. I'm very consistent. On average, I have during the Thursday 2 hour and 34 minutes, 35 minutes, 33 minutes. I surprised myself about that. Okay, everything is fine. So again, if you have doubt, drop me messages and well, not messages, but emails, and I will try to clarify your messages by email. If you are very specific and you drop also a picture of the problem of the formula that you don't understand, it makes easier for me to reply your mail. Okay, bye bye and have a nice weekend which is approaching. Bye bye.